Alright, physicists, welcome to our February 15th edition of physics. I hope you had a nice Valentine's Day. Here we are in my home office. There's my lawnmower handle. Okay, so today we're going to have one of our only two classes of physics this week, virtually, because this coming Wednesday is a reading day, so we don't have class this Wednesday. So we do have to go over quite a bit of stuff today. We're going to review what we did last week just a little bit, to talk about our Newton's three laws and how they were applied in last week's homework. Then we're going to push on and talk about frictional forces and centripetal forces. And then we're going to try to apply those ideas to some of the problems that I gave you for this week's homework. All right. So last week, the three big ideas were, of course, Newton's three laws. The first one is that objects in motion tend to stay in motion unless acted on by an outside force. So an example of a problem involving this was a pipe laid on a table, and once a ball rolls through the pipe and leaves the pipe, if it leaves the pipe, it continues to just move in a straight line. Keep in mind, we're seeing this from the top down. We're not seeing a ball being pulled down by gravity. We're just seeing that if it's on a frictionless surface and we don't have any other forces, it just keeps on going in a straight line at the same speed. So no forces means no changes in velocity. But if you're already moving, you get to keep moving. This is Newton's world. All right. So, what was Newton's second law? Newton's second law says that if we want to explain changes in the way that an object is moving, that is, if we want to explain accelerations, we have to introduce net force. And a net force has units of newtons, which are kilograms, meters over seconds squared. What does that mean physically? If you have a 1 kilogram weight, that's around 2.2 pounds, and you push on it with 1 newton of force, it will accelerate to a speed of 1 meter per second in 1 second. Okay? So, kilograms, that's this, to a meter per second in 1 second. So that's the physical meaning of a newton. And if we want to figure out what the net force is on an object, we have to take the sum of all of the forces on the object. So the reason why this is a little hard is that forces add like vectors. So you can't just add the numbers together. You have to do the whole thing where you figure out what direction the vector is pointing in. And if you want to add two vectors together, the easiest way to do it is by figuring out the x component of the vector, figuring out the y component of the vector, and then adding up all the x's, adding up all the y's. And then our third law is that each force is paired with a force that is equal in magnitude and opposite in direction. And so here's an example that we had last Friday in our lecture of a cantaloupe and a table, where we have two different paired forces where the cantaloupe and the earth are pulling on each other gravitationally. And we had another paired force where the cantaloupe is pushing down on the table and the table is pushing up on the cantaloupe with the normal force. And a couple distinctions that we made was that even though the normal force and the gravitational force are both pulling on the cantaloupe and are both in opposite directions, these are not a third law pair. Okay, those are both acting on the same object. They're not acting on different objects. And another point that I tried to make on Friday was that if you have, for instance, a person going forward, the way that they're able to go forward is that you push on the earth pushes on you, but in that case, the earth has a very big mass, you have a much, much smaller mass, and that's how you're able to accelerate, but the earth doesn't have any noticeable acceleration, even if in theory it should be just a teeny weeny tiny bit accelerated by you going forward. Okay, so Friday people took their quiz, 92% average. I'm happy with that. The problem that the most people got wrong was this one. It says the drawing shows a steel ball flying at a constant velocity from point A to point B in a region of space where the effects of gravity are negligible. During the short time that passes as the ball flies past point B, a magnet exerts a force on it in the direction of the magnet. Okay, so right here there's a kick where the force is going from the ball to the magnet. And it says, which of the following trajectories does the ball follow beyond point B? So the key issue here that I think is confusing is that when you look at this problem, you think of magnets as having a long range. And in this problem, they're asking you to suppose that the ball just gets a kick. So here the ball is going straight from point A to point B, gets a kick, poof, and then after that, no forces act on it. So if no forces are acting on it past then, it has to keep going in a straight line. So 2 has to be right, 1 can't be right because this changing direction, if it's not just going in a straight line, means that it's still accelerating. So there would still be a force on that. 3 would be the path that you would take if you didn't have any force. Nobody chose that. And then 4 and 5, 4 would be correct if it were being deflected from the magnet. That's not what the problem said. And then 5 has the same problem as 1 because the path is curved. Other than that, people did pretty well on the quiz. Okay, you do have a homework due today. I didn't get a lot of questions on the from people about last week's homework, and I can only assume it's because you were putting it off until this weekend. I don't suggest doing that. I think it's much better for you to try to get it done during the week when you can come into office hours and get some help, rather than putting it off until Sunday night, because there is quite a bit of work to do every week in this course. So here's, for instance, a question that I thought that I was going to get some cries for help on. I didn't. Maybe it's because it's easy. I don't think so, though. It says you have an electron with a speed of 1.2 times 10 to the minus, or 10 to the plus 7 meters per second. Okay, so that's about, I guess, 0.5% of the speed of light. Pretty fast. Moves horizontally into a region where the constant vertical force of 4.5 times 10 to the minus 16 newtons acting on it. The mass of the electron is 9.11 times 10 to the minus 31 kilograms. Determine the vertical distance and the electron is deflected during the time it has moved 30 millimeters horizontally. Okay, here's the tricky part about this problem. This is requiring us to remember stuff from last unit. What we learned last unit is that if you are talking about your x direction and your y direction, you can often split up the forces and split up the accelerations so that you just worry about the x direction and just worry about the y direction and don't mix them together. So for instance, in this one, you have an electron with a speed of 1.2 times 10 to the 7th meters per second. That is your initial speed in the x direction. And in your x direction, we are not experiencing any force, so I can expect my position versus time just to be this sort of thing. My position later is just my velocity times my time. And so if it tells me that it moves 30 millimeters horizontally, I can find out how much time this took because I know this, and I know my final x is going to be 30 millimeters, which is the same as 0.030 meters. Okay, so you can find out how much time that force was applied to to your electron in the y direction. Now, the other part is that you get to use F equals ma. This is a force in the y direction produces an acceleration in the y direction. So we've been given the force in the y direction, which is 4.5 times 10 to the minus 16th newtons. And we have the mass of the object, which is 9.11 times 10 to the minus 31 kilograms. Okay, so you should expect to get an acceleration that's pretty huge, right? So be prepared for that. The only conceptually tricky, there's not a lot conceptually tricky here, but the numbers are a little difficult to wrangle, because here you're going to get a time that's very tiny because the speed of the electron is very big, and here you're going to get a force that's really big because the mass of the electron is really small. Okay, so once you find that acceleration in the y direction, you can go ahead and find out how far your electron is deflected just using 1/2 at squared, and then the other terms v naught t plus y naught. This is going to be 0 because the initial velocity in the y direction is 0, and this you can use as 0 as well. And so you get your t from your x direction stuff, you get your a from your y direction stuff, and you want to find your y. Okay, and so your final answer, it's a vertical distance, so then it would be in meters, or if you wanted to put it in millimeters, you could do that. It'd be up to you. Okay, so that's a problem I think is a good one, but it's a little tricky. This week I did give you a couple of problems that were similar to last week's on your homework, just because I think that the ideas in them are worth dwelling on. We're still, everything in this unit is F equals ma. Force equals mass times acceleration. And finding the net force is going to be one of the big things that you're going to need to master before your next test. So here's a problem I gave you on this coming week's homework. Not due today, due 1 week from today. And let's just take a quick look at it. It says in figure 546, 3 ballot boxes are connected by cords, one of which wraps over a pulley having a negligible friction on its axle and negligible mass. 3 masses are 30 kilograms. Ma equals 30 kilograms. MB is 40 kilograms. MB is 40 kilograms, and then MC is 10 kilograms. When the assembly is released from rest, what is the tension in the cord connecting B and C? How far does A move in the first 0.250 seconds, assuming it does not reach the pulley? Okay, so I want to help you get a start on this. The way that you would start on a problem like this is to identify the forces acting on each mass. So for A, the forces acting on the mass are going to be the normal force pushing up on it, the gravitational force pulling down on it, and the tension force, and let's call that TAB. For object B, that's this mass, what forces would be acting on it? Well, this tension force TAB is pulling to the left on A, so it would be pulling up on object B, so there's your TAB. You also have it connected to another mass, so let's call that TBC. That's a different tension, a different string. And also acting on this would be the force of gravity, a different force of gravity. So this force of gravity, of course, would be ma times g, and the force of gravity on that one would be mb times g. So different masses for the different objects, different forces of gravities. And then for your object C, then you're going to have to go ahead and realize that it's being pulled up by the string right here. So you have your TBC, oops, pulling up, and then you have your force of gravity, which in this case is mass C times little g. Remember, little g is 9.8 meters per second squared, or 9.8 newtons per kilogram in each case. And so once you draw these pictures, you have to then try to convert it into an equation. How do you convert these into an equation? Well, each equation that you're trying to write down is F equals ma. So for A, we would have an equation in the y direction and an equation in the x direction. The equation in the y direction is not going to be very useful to us. It's just going to be Fn minus ma times g equals 0. We're not going to use that one. That's your y direction. The equation in the x direction is going to just be so maybe I should write this in a more consistent way. What we're writing down is F equals ma. So the F in this case in the y direction is Fn minus mag. So that's how I'm writing down my F net, and then equals ma times acceleration. Okay, now then in my but the acceleration in my y direction is 0, so that's where I'm putting the 0 in. Okay, now we don't need that equation because we know those are balanced forces if the block is not falling through it's not falling through the table. Okay, now in your in your x direction, you're just going to have the tension force, so TAB equals MA, that's 30 kilograms, times the acceleration. Okay, then I will write down also, so that's your equations for A. For B, what is your force equation? You're going to write F equals MA. So let's have up be positive and then down be negative. So in our y direction, we would have TAB, and then pulling down, we would have T minus TBC. Remember, we have a tension in this string, and we have a different tension in this other string. And then we'd have minus the force of gravity for this would be MB times G equals, and because this object would be accelerating downward, let's just keep our variables as positive, and I'm going to bring out the minus sign to say minus MB times A. Okay, so I have equations for A, I have equations for B, and then I have my equations for C. And my equation for C is going to be just these forces. TB pulling up, TBC pulling up, minus MC times G equals, and it's going to be accelerating downward once again, so minus MC times A. Okay, so essentially you have three equations, three unknowns. The unknowns are TAB, TBC, and A. And since you have three equations, three unknowns, essentially the problem is done. From that point on, it's just math. So we did the whole physics part of it. I want you to work through the rest of the math part. I'm asking you what's the tension in chord connecting B and C, so you want to find TBC. And I'm asking you to find the acceleration, basically, because I'm asking you how far does A move in the first 0.250 seconds. So you're going to have to use your acceleration and use one of your kinematic equations to finish the problem. Okay, so that's a little bit more of a challenging problem, but I think it is worthwhile to kind of put all these things together to use all of our tools. Okay, so that's basically the upshot of last week, is that we can use F equals ma in all sorts of fancy ways to connect the motion of particles, the acceleration of particles, to the forces on them. All right, now today we're going to try to move this a little bit closer to sort of real-world applications. And to do this, we're going to introduce two new ideas. The first one is the idea of frictional forces, and the second one is the idea of centripetal forces. And frictional forces are basically it's a little tricky to visualize, because all of the important stuff that's happening is happening at the microscopic level. From the big picture physics point of view, there are only 4 forces in the whole world. Okay, there's gravity, which is approximated by Newton's gravity. At some point, you need to start using general relativity. There's electromagnetism, and electromagnetism is everything else. Everything else in our normal life, from the fact that you can't smash your hand through the table, the fact that your cheeks are able to stretch, anything that's relevant to your everyday life, that's all electromagnetism. Then, deeper down inside the atoms, we've discovered 2 other forces. One is the strong nuclear force, and that's basically what keeps nuclei stuck together. So if you think about why is it that you can take 2 positive charges and stick them together inside of the nucleus, you have to come up with some really strong force to be able to do that. We call that the strong nuclear force. But sometimes you notice that you have things like radioactivity where nuclei decay. And so to explain that, you need to introduce another force, and that's the weak nuclear force. So if you have gravitation, electromagnetism, the strong nuclear force, and the weak nuclear force, those 4 forces are all of our fundamental forces in physics. But we're, in this class, dealing with sort of everyday examples of these, which manifest at a much higher level than those fundamental forces. So the frictional force is an example of a force that's at its heart an electronic force. When you have 2 objects sticking onto each other, they make essentially partial chemical bonds, and then when you start pulling on them, you need to overcome those partial bonds, and then once you break the bonds, you still have some dragging between those surfaces that still reaches a constant level. So we're going to have to worry about a static friction, that's the friction of objects that are not moving, and a kinetic friction, that's the friction of 2 objects that are sliding over each other. So frictional forces are going to be one of the things that we're going to do today. The other thing that we'll do today is centripetal forces. Now, centripetal forces are not a new type of force. They're a way that forces are being used. So if you have an object that's going in a circle, we already introduced that as centripetal acceleration, because if you're not changing speed, you're only changing direction. the acceleration is that v squared over r, the speed squared over the radius, and the direction of the acceleration is always towards the center. For centripetal acceleration, we're just making a little tweak on that, where instead of having our acceleration towards the center, we say, okay, to have an acceleration by Newton's second law, by F equals ma, there must be a force that's causing that acceleration. Okay? So a centripetal force is simply the force that causes the centripetal acceleration. And so that's not a new type of force, that's a way that forces are being used. Okay, so let's slow up and let's go back and look at friction in more detail. Okay, so as I said, friction is caused by microscopic electrical forces between two surfaces. Now, friction always opposes the direction of motion. And if you're sliding along a surface, the frictional force is something that's happening between the two surfaces. So if we're sliding in this direction, the direction of the frictional force always has to be directed parallel to the surface, opposite the direction of motion, which is parallel to the surface. Now, the thing that's a little bit confusing is that I'm going to give you an equation to model static friction, okay? But that equation doesn't give you the value of the static friction. It gives you a maximum value of the static friction. So, for instance, if I have a block on a rough surface and I push it with 2 newtons of force, right? And it doesn't move, it doesn't accelerate. That means that the frictional force in that case was minus 2 newtons. All right, so it'd be 2 newtons pushing back on me. Now, that value is not going to be captured in an equation that gives me the maximum value. Because if I put on 5 newtons of force, I would get back minus 5 newtons. And this is going to be true all the way up until I can break that object free and it starts moving. Okay? And if we want to, so let's before we even try to model it in a comprehensive way, let's see if we can just apply this idea to a general situation. Okay, so here's a general type of problem. In this problem, you have a 1 kilogram block that's placed against a wall and held stationary by a force of 8 newtons that's applied at an angle of 45 degrees, as shown in the drawing. And it asks, what is the magnitude of the friction force? So this is 8 newtons. Let's try to just figure out how to draw the free body diagram for this. What forces are acting on the block? Well, the one that we're given is this 8 newtons. Okay? And if I am canny, I realize that I'm going to have to split that up into an x component and a y component, which is going to be 8 newtons times sine of 45 and 8 newtons times cosine of 45, which those of you who are in the know will realize both of those are going to be square root of 2 over 2. All right, so what other forces are going to be acting on this block? It's a 1 kilogram block. Okay, so 1 kilogram. So if I know that and we're on Earth, there must be some force of gravity. Okay? So let's think. You're pushing it against the wall. What other forces are there going to be? There's also going to be a normal force. How big is the normal force going to be? Well, it's going to have to counteract whatever force you're pushing it into the wall with. And then it looks to me like you're going to need a little bit of frictional force that's actually holding it up in this case. Frictional force counteracts the direction of motion. So there's my force of friction. That's the if the block were going to be falling down, the force of friction would be pushing up. If the block were being pushed up, the force of friction would be going down. So it's always opposite the direction of motion. So there's my force of friction. Now, how would I set up the equation for how to find the magnitude of the force of friction? Well, I would write down force of friction. I would write down all my equations in the y direction. So in my x direction, I would have, here's my normal force pushing out perpendicular from the surface. I'd have Fn minus, and then this, let's put that, if I have my x direction this way and my y direction that way, in my x direction I would have minus Fn, because it's pointing in the minus x direction, plus 8 newtons times cosine of 45 equals 0. And then in my y direction, I would have my force of friction pushing out, and then this y component of that 8 Newton force would also be pushing up, so let's put that as 8 newtons times sine of 45 minus the force of gravity, so it would be minus m, so minus 1 kilogram times 9.8 newtons per kilogram equals 0. So what equation did I just write down twice? I just wrote down F equals ma twice. This is the sum of the forces in the x direction, and the acceleration, if my object is just staying still, is 0. So F equals ma. F equals ma. My forces in the x direction add up to 0. My forces in the y direction add up to 0. And so if you notice, right here you can solve for the force of friction. Okay? So if you do that, you should find that you get 4.1 newtons. So I encourage you to try it. This is these class problems are good practice problems to make sure that you're getting the right answer before you forge ahead to the homework problems. Okay, now a good way to model this static friction is, well, think about it to yourself. What's being modeled here is the interaction between two surfaces. Okay, you have the surface of the object sitting on a bottom surface, and how big is that force going to be? Well, it makes a lot of sense that the amount of force of friction is going to be somehow proportional to how much force is being pushed down or pushed up by the surface onto the object. So that's the normal force. So what we propose is that the maximum force of static friction can apply is going to be proportional to the normal force acting on the object. And so what we say basically is the force of friction, but the maximum is going to be some number times the normal force. And this number we call the coefficient of static friction. And I'm not sure, but I think you will be actually measuring this in lab with Dr. Galaba. Okay, so that's something to look forward to. All right, now notice that gives us the maximum amount of static frictional force. As I said before, if I put in 3 newtons and it's not moving, that means that my frictional force is going to be just 3 newtons. If I put in 5 newtons of force and I'm getting back no movement, that means that the frictional force is 5 newtons. So the magnitude of the frictional force is going up and up and up and up as I continue to push harder, up to some maximum value, and then your object will break free. It'll suddenly start accelerating. and then there'll be a different, smaller force that needs to be applied to keep it moving. So we're going to have one magnitude of our maximum amount of static friction, that's the frictional force applied when your object isn't moving, versus the amount that you'll get with kinetic friction. That's when your object is sliding. So let's do a quick example problem with static friction. This one is from your homework. And the only tricky thing in this types of problems is that you do need to worry about angles. Okay, so let's draw a picture. A 68 kilogram crate. Okay, as always, I draw it in the most artistic way possible with a dot. M equals 68 kilograms. Is dragged across a floor by pulling on a rope attached to the crate and inclined 15 degrees above the horizontal. Okay, so this angle is 15 degrees. There's the force that I'm pulling with. It says if the coefficient of static friction is 0.50, okay, so mu s equals 0.50. What is the minimum force magnitude required from the rope to start the crate moving? Okay, so let's see. In this case, we know what our force of gravity is because it's going to be m, that's 68 kilograms, times g. We don't know what the normal force is. That's the force pushing back up from the surface, and we don't know what the force of friction is. And so what we want to solve for, essentially, we're going to find our normal force. That's going to help us set up the force of friction, and that'll help us find what force we need to pull to overcome that maximum force of friction. Okay, so in the y direction, so what we're going to do is we're going to set up the F equals ma in the y direction, F equals ma in the x direction, and then solve for F. So in our y direction, our F equals ma looks like Fn pulling up plus F sine of 15 minus mg equals 0. So that's F equals ma. I'm adding up all the forces. I'm not accelerating in the y direction. In the x direction, my forces are going to look like, well, this force is pulling us forward, so that would be F cosine of 15 degrees. And then my frictional force is going to be going backwards, but let's just write that in terms of stuff that, in terms of our model. So I'm going to write minus our frictional force, which is mu s times Fn equals 0. Now, in this case, this is an equality because we're at that maximum force. Keep in mind that if I weren't pulling that hard, I wouldn't actually, my force of friction would just be counteracting the amount of force that I'm pulling with. But here, we're told that we're pulling it and we're just going to get it moving. So that's where we're getting this relationship. Okay, well, now it looks to me like I have two equations, two unknowns. I don't know my F. I don't know my Fn. And so I can just do algebra and go ahead and solve for, what is it asking? It's asking you the magnitude of the required from the rope to start the crate moving. Okay, so you're going to use your algebra and you're going to solve for F. Okay, so one thing you could possibly do is you could solve this for Fn and then put that in here and then solve by elimination, for instance. Then for part B, it asks, if this mu k is 30.35, what is the magnitude of the initial acceleration of the crate? Well, in that case, the idea is that you know what the normal force is going to be, and then if you know that normal force, but this number has changed, and you still know the force that's acting from that rope, then you're going to be able to use your F equals ma. Okay, so you're going to have solved for F cosine of 15 minus, and then this is going to be mu k times Fn equals m times a. Okay, so in the first situation, you're talking about static friction. In the second case, you're talking about kinetic friction. And because you're going to put in a different coefficient there, your mu k equals 0.35, you're going to be able to get out some acceleration. All right, so some tricky stuff to think about through that problem. Okay, now as I said, this idea of kinetic friction is that once you get moving, you have a lesser force, and that lesser force is modeled with the coefficient of kinetic friction, and then the greater force that's possible when it's just moving still is with your coefficient of static friction. And notice typically that the coefficient of static friction is bigger than the coefficient of kinetic friction. You get more friction from something that's just sitting still than once you get it moving. And you probably have noticed this if you're trying to push something across the floor. It's hard to get it moving, but once you get it moving, it's a little easier to keep it going. And so in your book, they discuss a little bit why that might be so, with electronic bonds having been made and it being more difficult to break those bonds than it is to continue to keep an object sliding over the transient electronic bonds that are being made. Okay? So let's just do one more example with this. In this one, we have a rainy evening. A truck is driving along a straight level road at 25 meters per second. The driver panics when a deer runs into the road and locks the wheels while braking. Okay, so usually on a car, you don't want to have this kinetic friction. When your wheels turn, you don't want your wheels actually sliding along the ground. You want them to continue to have that static friction where they're just rolling along. So if you get into a case with your car where kinetic friction comes into play, you're already sort of in trouble. But here's a case where a deer runs into the road and locks the wheels while braking. If the coefficient of friction between the wheel-road interface is 0.68, how far does the truck slide before it stops? Well, in this case, you would be using your F equals ma. Your truck presumably is not being pulled by anything extra, so the normal force and the gravitational force are just going to be equal. So Fn equals m times g. And the thing causing the acceleration in this case is going to be the frictional force. So the force of friction is ma, and so that ma is going to be mu times the kinetic the coefficient of kinetic friction times the normal force. So ma equals mu k times mg. Notice that the mass of the truck here doesn't come into play. And you can find out what the acceleration is going to be. So the acceleration is going to be 0.68 times 9.8 meters per second squared. From that point on, it asks, how far does the truck slide before it stops? Okay, well, in this case, you know you can use an equation like this one because you know the initial speed. You know the V naught is going to be 25 meters per second. You know that the final speed is going to be 0 meters per second. You know what the acceleration is, and you want to find that, you know, if you use 0 for your x naught, you want to find your x. Okay, so that's another good type of problem that you can do with this. I will let you finish that problem. The answer you should get is 47 meters. So give it a shot. See if you can finish that one, and hopefully that'll give you a little bit better understanding of our kinetic friction model. Okay, our second big idea for today, I don't want to spend as much time on. We're going to use the idea of centripetal force. And as I said, centripetal forces are not a new type of force. It's just a force that's causing a centripetal acceleration. So our centripetal acceleration, remember, it's an acceleration towards the center of a circle, and it has a magnitude of v squared over r. R is the center of is the radius of the circle. V is how fast your object is going around the circle. So if you have F equals ma, and your acceleration has a size of v squared over r, your centripetal force must have a size of mv squared over r. Okay, so as I said, this doesn't define a new type of force. It's just a way that forces might be used. Okay, so here's an example. I think it's a good one. It says, in figure 6.39, a car is driven at a constant speed over a circular hill and then into a circular valley with the same radius. At the top of the hill, the normal force on the driver from the car seat is 0. The driver's mass is 70 kilograms. What is the magnitude of the normal force on the driver from the seat when the car passes through the bottom of the valley? All right, so here's the thing to realize. The only forces at play here are the normal force and the gravitational force. In this case, what force is drawing that car towards the center of the circle? Well, we're told that the normal force is 0, so that full force has to be the gravitational force. On the other hand, down here, you need to push pretty hard because you're going to have a big normal force that has to counteract the force of gravity and still provide that acceleration towards the center of the circle. So Fn and Fg they're not balanced in this case. It says, what is the magnitude of the normal force? Well, in this case, for the first part, you're going to use this one to solve for the speed of the car. Okay, so you're going to say that the centripetal force in the first case is just the gravitational force. It's just mg. So my mv squared over r equals m times g. In your second case, you have the normal force and you have minus the gravitational force equals mv squared over r. Okay, so this is F equals ma, but the a is going to be, again, centripetal acceleration towards the center of a different circle. All right, so I think you can maybe see where I'm going with this, which is they want you to find Fn, which in this case is going to be Fn minus mg. If this circle has the same radius as that circle, I can go ahead and use this mg equals mv squared over r. And my normal force is just going to be 2 times mg. So an interesting thing in this case, you would feel like you had 2 g's of acceleration on you. You know, when you see Air Force movie or something, they're talking about the g's. In that case, you would feel 2 g's because you'd feel double your weight. You'd feel the Earth pushing up on you twice as much as it usually does. So in this case, if you have 70 kilograms, the force you would feel is not around 700 newtons. You'd feel around 1,400 newtons. Okay, so a little tricky. Let's do one more example with centripetal acceleration. In this case, a cat dozes on a stationary merry-go-round in an amusement park. And the point I'm trying to make here is that the centripetal force is just the force that's acting towards the center of the circle. It doesn't have to, it doesn't necessarily have to be the normal force. It doesn't have to necessarily be the gravitational force. It's just whatever force is acting towards the center of a circle. So in this case, the frictional force is going to act as the centripetal force. Okay, the radius of 5.4 meters. So there's r from the center of the circle. Then the operator turns on the ride and brings it up to its turning rate of 1 complete rotation every 6 seconds. So that gives me the period of rotation is 6.0 seconds. As you hopefully remember from our last outing with circular motion, the way that you find the speed is going to be to take the circumference divided by that amount of time. So 2 pi r over t. You have r, you have t, so we can find how fast the kitty is moving. And it asks, what is the least coefficient of static friction between the cat and the merry-go-round that will allow the cat to stay in place without sliding? Okay, so effectively that force of friction is going to be the centripetal force. So you're going to write mu static times Fn equals mv squared over r. So the centripetal force is equal to mv squared over r. And so Fn in this case would be the just the mass of the kitty times the gravitational field strength. And so in this case I would write mg. And notice I haven't been given the mass of the cat, but that doesn't matter because I can divide both sides by the mass. And then I can divide both sides by g to find mu s. Okay, so that's kind of the logic that you should expect to see in these types of problems. Okay, so what have our big ideas of today been? 1, static friction is the force that keeps objects that are not moving from starting to move. 2, kinetic friction is the force that stops moving objects from continuing to move. And 3, forces that cause objects to move circularly can be classified as centripetal forces. Okay, so please take a look at your homework, and thank you for watching.